Okay, so now we've defined what it means to be a linear combination of vectors, and thus we've gotten at what it means to be in the span of a set of vectors. So let's consider a couple of examples. Here we're working in R2. So if we want to consider, well, what vectors are in the span of the vector 2, 1 and the vector minus 1, 1? Well, this we looked at on in a previous video. And if you recall, that was this video where we had a bunch of diagonal streets like this. And we were trying to give directions where the streets were either parallel to the vector 2, 1 or the vector minus 1, 1. And we saw that we could wind up anywhere in the plane taking some linear combination of these two vectors, since we don't need the scalars to be integers. So I can get anywhere in R2 by walking along these directions. So the span of those two vectors would be all of R2. So now if we, in addition, have this vector and this vector 2, 1 and minus 1, 1, and now I add a third vector to this set 1, 0, and we ask, well, what is the span of this set? Well, when we're combining vectors in R2, all we're going to get out again is going to be some vector that has the same dimension. So this entire set has to be contained within R2. So it's impossible for me to get a vector in R3, for example. So I can get anywhere that I want in the plane R2 by taking some combination of these two vectors. So adding in the third vector doesn't add any additional vectors to the span of this set. We already can get all of R2 from the first two vectors. So by adding in this additional vector 1, 0, I haven't changed the span of this set. In question 3, we now want to think about, well, what is the span of the set containing the vector 2, 1 and the vector minus 4, minus 2. And so here, there's something really special about these two vectors, and that is minus 4, minus 2 is equal to minus 2 times the vector 2, 1. And so if I were to kind of look at this, similar to how we were thinking about directions in a city, well, the vector 2, 1, that sits over here someplace. And the vector minus 4, minus 2, well, that sits over here someplace. But they sit on the same line. And I would not be able, for example, to wind up at some point over here or some point over here. So the span of these two vectors is a one-dimensional thing. I can only wind up on some point on this line. So the span of this vector, of these two vectors, in other words, would be something that sits along the line y is equal to 1/2 x. So in this case, we don't get all of R2. We get just a subset of R2 of all of the points that sit on that line. And in the fourth question, we're asked to think about, well, what is the span of the 0 vector in R2, 0, 0? And so in this case, we don't have any magnitude at all. We don't have any vectors. So the span of that set would just be the vector 0, 0 itself. And that I can indicate with just a vertex drawn at the origin, since that vector has no magnitude. So this actually has no dimension. It just consists of 1 point. So if we're working in R2, what we can see is, given a set of vectors, the span of that set of vectors could possibly be all of R2. It could be a subset of R2, which is a one-dimensional line, or perhaps it might just contain 1 point, in which case it's like a zero-dimensional space.